Hi everyone, this is the video for Solubility Product. There's only one part, so there's only one video. It is in chapter 6 and we start with section 6.4 on page 131. Alright, let's get started. So KSP is the equilibrium constant for reactions in which a solid salt dissociates into solution. SP stands for obviously solubility product. So again, we already know what equilibrium constants are. Now we know what the symbol is for a reaction that actually has a salt that's dissociating into solution. That's called the KSP. There's a list of solubility products in Appendix A. I suggest that you look in Appendix A and make sure that you know how to find compounds and that you can read through the different charts that they have there. So for this example, I'm giving you lead 2 iodide is in equilibrium with its two ions that it's dissociating into, Pb2 plus and iodide. So if I wanted to write the equilibrium constant for that reaction, I would take the products over reactants. But of course, we don't include solids. We know that already. So that's why there's nothing on the bottom of that fraction. But you have Pb2 plus, because you only have one of them. And then how many iodides do you have? You have 2. So that's why they had the little superscript 2 next to the I. If you go to the back of the book in the appendix and find iodides, and look specifically for the one that says lead iodide, you'll see that the number right next to it is 7.9 times 10 to the negative 9. So a solution is said to be saturated when the solution contains all the solid that's capable of dissolving. That's what solubility product tells you. It tells you how soluble this solid is in this solution. What if I asked you what the concentration of Pb2 plus was in a solution that was saturated with lead 2 iodide? We would use the equation, obviously, that I just showed you in the last slide. So it's lead 2 iodide as a solid is in equilibrium with both of its ions. The initial concentration of those 2 ions are 0 because you have just that solid. Now, what happens at the final concentration? The final concentration, the solid stays a solid, and what has dissociated? What dissociated was X, the Pb2 plus, and then of course the other X, which is your iodide, but you have a coefficient there, right? So that's actually 2X. So this is when these charts become important because you have to really make sure that you look at your balanced reaction and make sure that you put everything that you need to put down in these charts. So you have X for Pb2 plus because there's only 1 mole of that lead ion. You have 2X because there's 2 moles of that iodide. Now you write your KSP equation. We already saw it. It was lead 2 plus times iodide. But that superscript, because there's 2 of them. All right, so that equals 7.9 times 10 to the negative 9. So now I'm going to make my general equation to try to solve for X. So my lead is X, and then my iodide is 2X squared. Now let's put all those X's together. That would be 4X cubed. So 4X cubed is equal to 7.9 times 10 to the negative 9. If you solve for X, well, first you have to divide by 4. If you divide by 4, you get 1.975 times 10 to the negative 9. And then you take the cube root of that number, and you should get 1.25 times 10 to the negative 3. So what does that mean? That means that the concentration of the lead ion in that equilibrium reaction is 1.25 times 10 to the negative 3 molar. Whereas your iodide concentration is twice that because it's 2X. So that's 2.5 times 10 to the negative 3 molar. There's nothing different here that we don't know how to do from our previous equilibrium problems. Only thing is that now you have a solid, so that solid does not get included. And also you have to really pay attention to the reaction and really pay attention to the molar coefficients of these things because that has to go into your chart. This is not an acid-base conjugate anymore, so it's not always a 1-to-1. It depends on the balancing, the correct balancing of your reaction. Let's talk about what the physical meaning of solubility product really is. If you leave water in contact with excess salt, for example, excess PbI2, that solid is going to dissolve until it meets that value of solubility product. In other words, it's going to keep dissolving until that KSP value is satisfied. Because after that is satisfied, after that value has been reached, no more solid is going to dissolve. So when and only when that value has been satisfied and all the solid has dissolved, once you reach that spot, like I said before, that's when you're actually going to start seeing precipitation. So in essence, the KSP tells you how much concentration of that solid is able to dissolve before you actually start seeing a solid coming out of solution. So let's say you had a solution of PbI2, there's really no guarantee that it has met the solubility product, that it has met that KSP value. But of course, that isn't the only thing. Right now, KSP doesn't really tell the entire story. The concentration of undisassociated things or undisassociated species may be really significant in these types of solubility problems. So let's consider what happens when you have a second source of iodide and you add it to a solution that's saturated with PbI2. Remember, the solubility of PbI2 is going to be affected by anything that you add into this solution. So for example, if I was to add a separate source of iodide into that solution, it's going to shift the equilibrium of that reaction. In effect, that's kind of like a reflection of Le Chatelier's principle. But let's go ahead and add this 0.030 molar NaI, which we know will dissociate completely into its ions. What happens to the concentration of Pb2+ in that solution? If we do that, and we set up our table just like we did before, everything looks the same. The only thing that's different here is that now we're going to add an extra source of iodide, 0.030, and I reflect that here in my initial concentration of iodide, and then in my final concentration, it's X for Pb2+ and 2X for your iodide, just like before, but it's 2X plus that extra source of iodide. So now we bring that down here to the equation of equilibrium, and you see that it looks kind of ugly. So what we have to do, and this goes for not everyone, but mostly the problems that you're going to be doing, it's gonna be the same sort of story. You have to kind of think about the size of X. Remember that X was 1.25 times 10 to the negative 3 when we didn't add any iodide. That was the problem before. It was really small. It was 0.00125, right? So if we add more product, right, because if we're adding an extra source of iodide, which happens to be a product, that's going to shift that equilibrium, and that's to the left, and that's also going to mean that less Pb2+ is going to be dissolved because you're shifting the equilibrium to the left. So that means, of course, that the concentration of X, which is your Pb2+, is going to be less. So now, since I'm adding an extra source of iodide, I know that my 2X is going to be way smaller than my original X, or for that matter, my original 2X. So to make this equation a little bit simpler, because of that assumption that we're making, why don't we go ahead and disregard the 2X? Because I know, I'm suspecting that 2X is going to be way smaller than what I've added, that extra little bit that I've added, which is that 0.030. Because again, we're adding a product, so that equilibrium is going to shift towards the left, which also means that you're going to have a less dissolved concentration of your Pb2+ ion, which is your X, which also means that it will be less for your 2X concentration. All of it is related. So now if we went ahead and removed that 2X because of our awesome, super smart assumption, look how simple this equation becomes. It's just the X times the 0.030, which was added, and of course that's squared because of the iodide, the molar ratio. And that equals to the KSP of PbI2. If you solve for X, it's a very simple equation. You get 8.8 times 10 to the negative 6. Look at that number. That number is way less than what we originally got for our X when we didn't add any iodide. it was like 0.00125. This is 8.8 times 10 to the negative 6. So that 2x was indeed much smaller, much smaller than that 0.030. So our assumption was correct. So the take-home message here is that you will probably be able to do this in every problem that you do in my class, not necessarily meaning that it's every single time in every problem like this that you ever do in your life. But in my class, more than likely, that's what you're going to be expected to know. And of course, always as a check, you should go back and make sure that your assumption was correct. Make sure that the number that you get for x is way smaller than what was added. Because if it isn't, then maybe your assumption was not too good to make in the first place. So that is what we know, what we call the common ion effect. Let's see if we can do this problem. It says, find the concentrations of Hg2, 2+, and iodate in a saturated solution of mercury 1 iodate if there are no other significant species such as the ion pair Hg2, 2+, and IO3-. And of course, they give you the equation or the reaction right at the bottom here. So the first thing you have to do is figure out, go to the back of the book, go to the appendix A, and figure out what the KSP for that mercury 1 iodate is. So you have to look for iodates. If you do that, you'll find that the KSP is 1.3 times 10 to the negative 18. If we write our little table, which probably you don't even have to anymore, you'll see that you have a solid at the beginning, and at the initial concentration, Hg2+ is 0, and of course the iodate is 0. At the final concentration, your solid is still a solid, and you're going to have X for your Hg and 2X for your iodate. This is already starting to become old news. We go ahead and make the equilibrium equation, and you should get X times 2x parentheses squared is equal to 1.3 times 10 to the negative 18th. If you solve for x, you should have gotten 6.88 or 6.8 times 10 to the negative 7th molar. Remember that 2x all is under the parentheses, so that really becomes 4x squared. So you go ahead and divide that number by 4, and that's how you would get the 6.8 times 10 to the negative 7th molar. So that's the answer to that part of the problem. The second part of the problem says, find the concentration of the mercury ion, or the mercurous ion, in a 0.01 molar solution of KiO3 saturated with that same solid. So here is an example of the common ion effect. We're adding a separate source of iodate into this solution. So if we do our table, at the beginning, you're going to have solid for your solid, 0 for your Hg2+, and then you're going to have 0.010 for that iodate, because that iodate is initially in there because you've added it to the solution before anything has happened. The final concentration is, of course, going to be solid, still stays as a solid. The Hg2+ becomes your X, and your iodate is now 2X plus 0.01. If we write our equilibrium reaction or equilibrium equation, you would really write your KSP is equal to X times parentheses 2X plus 0.01 close parentheses and that squared. Now comes the reasoning, the assumption that you have to make. Remember what X was without any addition of any of the iodate. It was 6.88 times 10 to the negative 7th. You're adding 0.01. So I'm going to assume that 2x, because I'm adding more product, is going to shift the equilibrium to the left, which means I'm going to have less dissolved Hg2+ and less dissolved iodate. So therefore, I'm going to go ahead and make the assumption that I can go ahead and remove that 2x. Makes this equation way simpler. So now all I have is x times 0.010 squared. Ends up being, if I go ahead and solve for all of that, you should get 1.3 times 10 to the negative 14th molar. And look at that number. That number is way less than 0.01, which is what I added into the solution. So our assumption was correct. So there you go, guys. That is your second example for the common ion effect. This is essentially all you need to know for your second exam, and I will see you guys later. Study hard. Bye-bye.